Hi guys, and welcome to HSC Chemistry topic production of materials. In this video we're going to be focusing on nuclear equations, how we represent nuclear reactions using chemical notation. So this is yet another way of writing or simplifying how we represent what happens in different interactions within an atom. We've looked at a lot of different ways of writing chemical reactions, molecules and equations in the past. This is another type with the same basic rules, and that is that we've still got to make sure that everything on both sides of the arrow is balanced. So nuclear equations are a common way of demonstrating what is happening. We need to make sure that we balance the atomic numbers, which we're going to be regarding, I guess, as the charge. So this is equivalent to the number of protons, and hence sometimes we can have a negative number there. And this number is the mass, so the total mass. And both of these numbers need to be equal on either side of the arrow. So if our total on this side is 263, then we must have 259 plus 4 to equal 263. And that's these two numbers here. Likewise, the number on the bottom, 106, must also be a result of 104 plus 2 to equal 106. Now this is a type of alpha decay, so you can see that this is the helium nucleus, so that is alpha decay that's occurring in the first one. And in the second one we've looked at before is carbon-14, which is breaking down into nitrogen-14 with the release of a beta particle. And once again, 7 minus 1 is 6, so that's all right, and 14 plus 0 is 14, so that's all right. Be aware of the fact that when you're looking at these equations, that as long as you know what type of decay is occurring or what type of atom is being produced, you can infer what else is happening just by making sure that you balance both the charge and the mass. So then if we're going to have a look at some nuclear reactions, then it's important to make sure that we've got a couple of examples of each of these. So this is the radioisotope radium-226, which decays by alpha decay into radon-222. We know that this is likely to be an alpha decay because of the size. So remember, there's three reasons why isotopes may be radioactive, and that is because they have too many neutrons to protons, they have too few neutrons to protons, or just because they are very large atoms. And this is an example of a very large atom. So on the left side of the arrow we have a mass of 226 and an atomic number or a charge of 88. So we need to make sure that these are balanced on the other side. So we have 4 and 222 and 2 and 86. So in this case they are balanced. You'll find that often these symbols A and for mass number and Z for atomic number are used, and so it makes it a little bit easier to talk about these in general terms. So for alpha decay, the mass number is going to decrease by 4 and the atomic number is going to decrease by 2. So we've had a go at this already, but can you write the equation for the alpha decay of uranium-238? Well, if I just told you this, you could find out from the periodic table that the atomic number for uranium is 92, because we get that directly from the periodic table. So then what we need to do is identify what happens when this particular product decays through alpha decay. We know that alpha decay is a helium nucleus, so therefore it's going to have the number 2 and 4. And the other product is going to ensure that we have a balance in the number of both charges or protons and the mass. So we need to make sure then that we have 90 as our number. 90 plus 2 is 92, and that corresponds to the element thorium. And the mass of thorium, in this case, the particular isotope of thorium is thorium-234, and 234, and 4 gives us 238. So we've made sure we've balanced our equation here. Now, another type of radioactive decay is beta emission, and beta emission can occur in nuclear reactors. And one of the examples of this is uranium-239. So there are a number of different isotopes of uranium, and because uranium is such a large element, large atoms, they're all going to be unstable and break down. But they don't all break down by alpha decay. This particular one breaks down through beta decay. And so in this case, we need to again look at the numbers that we have on the left, 239 and 92. And we need to make sure those numbers are balanced on the right. Now, a beta particle, being an electron, has a negative charge and no mass. So it means that our mass will be the same, 239, 239, but our atomic number, our charge, will actually increase by 1 and move up to 93. And so this will produce the element neptunium. For beta decay, the mass number does not change. So there's no change in mass in this case, but the atomic number actually increases, goes up by 1. This is one we've done before, and we've been through this in class, so it should be fairly straightforward for you to follow the process of what happens when carbon-14 breaks down. So carbon is 6. It's going to break down through beta decay, so we're going to have an electron with a -1 charge and no mass, and it is going to create something with an atomic number of 7. 7 minus 1 is 6, and that is nitrogen. And because the mass doesn't change, it'll be nitrogen 14. And this is our beta particle. Now, the third type of radioactive decay is gamma emission. Now, the thing with gamma emission that makes it slightly different from the others is that there is no change in either the mass nor the charge. This is not a particle, but a quantum of energy that's actually being emitted or released from the nucleus. So we need some sort of indication that this is what's actually happening here. Can't see the arrow very well here, so I'll draw it in for you. This is the problem with this type of decay, is that you can see that there's actually been no change to the actual element itself. It's the same as it was afterwards. We just have the gamma radiation being released as a consequence of this. So this sort of type of radioactive decay can occur on its own when we just have some slight excess of energy that we want to try and release, or at least the nucleus wants to try and release in order to stabilize its energy levels. So one of the things that we are trying to do, I guess, is to try and determine why certain atoms are radioactive or unstable, and what sort of radioactive particles they're likely to emit. So often the radioactive nucleus of heavy elements cannot become stable through a single emission. And we have looked at this again through the uranium decay series, where the nucleus is very large, larger than about 82, 83. If it's just a little bit larger, then we can have an alpha decay that can bring it back into a stable size. But if it gets much bigger than that, and some of the very large ones that have been discovered more recently are very, very large atoms, and so they often go through a sequence of emissions in order to reach stability. So a lot of the products tend to be intermediate. The product itself may well be unstable, and it will radioactively decay to another product, which itself may be unstable, and so on, until we reach a stable nuclide, or a nucleus which is no longer emitting radiation. When this happens, we call this a decay series or radioactive series. So it's not a simple step. It's not just one decay product. It is a series of decay products. And perhaps the best example is the uranium-238 series. So For each of the arrows, it's important that you can identify the type of decay that's occurring and write an equation to describe the decay. So in this case, uranium-238 is undergoing an alpha decay in order to form thorium-234. Then there are 2 beta particles, and then there is 1, 2, 3, 4, 5 alpha particles, 2 beta particles, another alpha, 2 beta, and a final alpha. If we were to write the equation to describe this decay, we would start with our initial substance, which is uranium-238. What we have is 1, 2, 3, 4, 5, 6, 7, 8. 8 alphas to 4 alphas. You can call them helium nuclei. We have 1, 2, circle those 1, 2, 3, 4, 5, 6. So 6 minus 1, 0 electrons. And our final product, which is lead, Pb, 82, and 206. Now we need to make sure that all of these balance up, and I've kind of written in a way that makes it hard for us to see that. But we've got to have 92, well, we've got 92 on the left, so we've got to have 92 on the right. So I have 82. I'm going to subtract 6, so that's going to be 76, and then I'm going to add 16. And so that becomes 92. So I did that right. Let's see if the masses add up as well. So I need 238. I have 206 from the lead. I have no contribution from the beta decay, but I have 8 4s are 32 from the alpha decay. So I have 2, 3, 8, and it's all balanced. So it's probably worth writing this equation out somewhere where it's a little bit easier for you to see. So the 238 92 uranium has decayed into 8 alpha particles and 6 beta particles and 1 atom of 206 82 lead. So this is the summary for the decay series of uranium-238. Thanks for watching.